Welcome back. I hope that you have managed in making the chapter 1 exercises, and for the Utrecht University students also the Blackboard individual exercises. We will continue now with chapter 2, the chapter on atmospheric water. This is for the Utrecht University students with regard to the Wereld Draait Door small exercise and video. We observed the sun to rise in the east and to set in the west. This is due to the Earth rotating on a daily basis. So when we observe the sun to rise in the east and to set in the west and think of the sun as being stationary, in actual fact your Earth is moving from west over south to east. So when we look upon the northern hemisphere from space, the Earth rotates from west over south to east, thus anti-clockwise. But in the Wereld Draait Door video, the Earth is seen to rotate clockwise when observed from above the northern hemisphere. So this is incorrect. And it's important to recognize this in order to understand why the Coriolis effect, which we will discuss in a minute, causes air movement from our perspective at the Earth's surface to experience a deflection to the right on the northern hemisphere and a deflection to the left on the southern hemisphere. I also asked the Utrecht University students to look at the two Coriolis effect videos at the equator on Blackboard, and you can or should have questioned yourself the following. A. Both videos tell the truth. B. Only video 1 tells the truth. C. Only video 2 tells the truth. D. Neither video tells the truth. The answer or major conclusion to be drawn will be provided on Blackboard, but after attending this lecture, you hopefully will know what the right answer should be. There is a nice video on the online resource center, the web links, as well as on Blackboard. It shows you the Coriolis effect at the northern hemisphere, and for this a merry-go-round is used, een draaimolen. The merry-go-round is rotating anti-clockwise. De draaimolen draait tegen de wijzers van de klok in. You're sitting here, holding a ball in your hand, and your friend is sitting there, more near the center of the merry-go-round. You and the ball are experiencing large velocity in this direction, but your friend, because he's more near to the center, is experiencing a lower velocity in that direction. You're rolling the ball towards your friend. Your ball still holds that larger velocity, but is moving into areas where the disc is rotating at a lower velocity. So your ball will curve to the right. Now think from your friend's perspective, and your friend is also going to roll a ball towards you. So the ball holds a small velocity in that direction and will be rolled to you, and here there are larger velocities in that direction, but the ball will still hold the lower velocity, and this also means that the ball will curve to the right. And exactly this is also what's happening with the movement of air parcels on the northern hemisphere. And when you want to tell the story for the southern hemisphere, of course, then the Earth is rotating clockwise when observed from down under space, and there you get a deflection to the left. Here we have a situation high up in the atmosphere. The picture given here is a plan view, so a horizontal view. High up in the atmosphere, there's no friction. Air wants to move from a higher energy to a location with a lower energy. We're looking at the same height. This means that air wants to move from a higher pressure to a lower pressure. Here we have an isobar of 512 millibar, which is 512 hectopascal, and here we have an isobar of 500 millibar, 500 hectopascal. Air is moving in this direction due to the pressure gradient force, but as soon as the air starts to move, the Coriolis effect will come into action and will cause a deflection to the right. You can see that the Coriolis effect is indicated here as a force, which is not totally correct, I should say, but for this presentation, just think of it as a force. You see that there is a deflection to the right, which continues, and it continues until an equilibrium status is attained. And in the equilibrium status, your wind is blowing parallel to the isobars, and your pressure gradient force and your Coriolis effect are counteracting each other, so are balancing each other out. This wind is called the geostrophic wind. You can experience this, for instance, when you fly in an airplane from, for instance, New York to Amsterdam. The geostrophic wind will act as a tailwind and will make your journey shorter than when you're flying from the other way, when you're flying from Amsterdam to New York. We know this geostrophic wind as a jet stream. These jet streams, there are actually 2 in the northern hemisphere and 2 in the southern hemisphere, are at an altitude of 9 to 10 kilometers. The jet streams are 6 kilometers wide and they meander over a width of 200 to 800 kilometers. And here you see the subtropical jet stream, also in the southern hemisphere, and the polar jet stream, also in the southern hemisphere. This picture shows you the atmospheric circulation on the northern hemisphere in cross-section view. Here we have the equator, here we have the North Pole. The Earth receives much heat at the equator and very little at the poles. This causes transport of heat in the direction of the poles and transport of cold air from the poles towards the equator. Because of the Earth's rotation, the Coriolis effect, and also the uneven distribution of land masses and oceans, a number of global circulation cells are created. The Hadley cell, the Ferrel cell, and the polar cell. At the equator, warm air rises and starts to flow in the direction of the poles at an altitude of about 15 kilometers. At latitudes of about 30 degrees, the air descends. In the northern hemisphere, this descending air is responsible for deserts such as the Sahara and the buildup of the semi-permanent Azores anticyclone, het Azore hoge drukgebied. This figure shows this descent of air splitting at the Earth's surface. Part of it is flowing back to the equator, whilst another part continues its route towards the poles. Meanwhile, at the poles, cold air sinks and is transported over the land surface in the direction of the equator. In the mid-latitudes, around 60 degrees, cold air from the poles and warmer air that has continued its route towards the poles meet, as shown in this picture. When cold and warm air meet, frontal precipitation is formed. And here we have air which is rising, which can lead to convective precipitation. And here we have the polar jet and the subtropical jet I told you about in the former picture. Here we have the same picture that we were just looking at, so the atmospheric circulation on the northern hemisphere. And this picture shows you the overall three-dimensional view. So here we have the equator. You have winds in the direction of the equator with a curved deflection to the right. Here we have the mid-latitudes, and here we have westerly winds. And here typically we have the area where cold polar air meets warmer air from the south. What is also important with regards to the distribution of heat over the Earth and also for the climate is what is happening in the oceans. And there we have an ocean conveyor belt circulation where you have cold deep currents, which are indicated in blue, and warm shallow currents that are indicated in red in this picture. Warm ocean water travels from Florida, from about here, in the direction of northwest Europe. On its journey, the warm ocean water becomes more saline due to evaporation. Direct cooling of this saline water by air south of Spitsbergen further increases the density of the water, causing it to become heavier than the water below it, and to sink to greater depths, from where it is carried as a deep cold return flow southwards to the tropics again. Because of the Gulf Stream, this is the Gulf Stream, and North Atlantic drift, winters in Western Europe are relatively mild, especially compared to the winters at the same latitude in Western Canada and Alaska. Earlier on, we discussed what happens in the upper atmosphere. You have a counterbalancing of your pressure gradient force and your Coriolis effect, and this causes the wind to flow parallel to the isobars. But that's a situation where you have no friction. When you're at the Earth's surface, you have friction. So a kind of same mechanism applies because you're at the same height and air wants to move from a higher energy to a lower energy. It moves from higher pressure to lower pressure. This gives you the pressure gradient force. And as soon as the air starts to move, your Coriolis effect comes into play. And then on northern hemisphere, this means a deflection to the right. But when you're at the Earth's surface, there is another force which comes into play, and that's friction or resistance, the friction force. Your Coriolis force at the northern hemisphere is to the right of your movement of the air, and your friction is always opposing the movement of the air. So also at the Earth's surface, you will attain an equilibrium situation, but the equilibrium situation will be slightly more complicated than what you have in upper space and looks like this, the picture that you're looking at now. So we have a high pressure here, we have a lower pressure there. This is your pressure gradient force, and then not only the Coriolis effect, but also the resistance force, the friction force come into action. And the equilibrium, you can see if you take the resultant of these two forces, think about Coriolis as a force, then this is the resultant. And in an equilibrium situation, the situation that you attain, this resultant force is equal to your pressure gradient force. But now you see that the air movement is not parallel to the isobars, but at an angle to the isobars. This is known as the Buys-Ballot's law. The Buys-Ballot's law states that in the northern hemisphere, when you stand with your back to the wind, so your back is in that direction, you're facing that direction, then low pressure is in front of you to the left, and high pressure is at the back of you, behind you, to the right. Of course, when you're in the southern hemisphere, the Coriolis effect is to the left, deflecting to the left, and then Buys-Ballot's law would read, when you stand with your back to the wind, low pressure is in front of you to the right, and high pressure is at the back of you to the left. Buys-Ballot, by the way, was the first professor in physical geography at Utrecht University. So air movement at the Earth's surface is at an angle to the isobars. On the northern hemisphere, this causes the flow of air around the low pressure area to be spiraling inwards as indicated on this picture. The air does so in an attempt to counteract the low pressure at the center of this low pressure area. Importantly, this converging air movement near the Earth's surface can only take place when there is a possibility for the air to escape upwards from the center of this low pressure area. In the center of a low pressure area, the air rises, expands, and cools, causing the formation of clouds by condensation at a higher level. Precipitation associated with this convergence and uplift of the air is called cyclonic precipitation. The movement of air around and in high pressure areas, shown here, is the opposite of what happens around and in low pressure areas. The air movement in the center of the high pressure area is downwards, and then the air movement spirals out of the high pressure area as indicated here. So on the northern hemisphere, we get an anti-clockwise movement around low pressure areas and the clockwise movement at the Earth's surface around high pressure areas. And of course, in the southern hemisphere, this is the other way around. Clockwise around low pressure areas and anti-clockwise around high pressure areas. This picture shows us the Clausius-Clapeyron relation. On the vertical axis, we have the saturation vapor pressure. Not only does air exert a pressure, but also the water vapor in the air exerts a pressure. And we call that the actual vapor pressure. And if the air is fully saturated with water vapor, we talk about the saturation vapor pressure. The vapor pressure is expressed usually in kilopascals. So here we have the saturation vapor pressure, here we have temperature. And you can see warm air can contain more water vapor, so at a higher saturation vapor pressure than cold air. What you can also see is this curve is for water and the broken line here is for ice. So ice has a slightly lower saturation vapor pressure than water. Well, let's talk a little bit about cloud formation. Heating of the land and of the air directly above the land causes the air to rise, a direct result of a heated pocket of air being less dense than the air surrounds it. The air, when it rises, cools down. This is simply a consequence of the heat being distributed over a larger column of air. The upward movement of the heated pocket of air continues until at some greater height, the pocket of air cools down to the temperature of the surrounding air, which then effectively holds a further upward movement of the air. Heating of the sea or of wet land surface causes evaporation and now moist air to rise. Cool air cannot hold as much water vapor as warm air, as already indicated in this Clausius-Clapeyron relation. Saturation vapor pressure is the pressure exerted by water vapor molecules in the air when the air is saturated with water vapor. At some greater height, the continued cooling of a rising pocket of moist air may cause it to become saturated with water vapor before it reaches the same temperature as the surrounding air. The relative humidity of the air is then 100%, and the temperature has reached its dew point if this temperature is greater than 0 degrees Celsius, or its frost point if the temperature is 0 degrees Celsius or less. At the dew point, condensation starts. This means that part of the water vapor in the rising air turns into liquid water, which is visible as a cloud. Likewise, at frost point, deposition starts, which is the change from water vapor to ice without passing through the liquid state, and which is also visible as a cloud. So a cloud can be defined as a visible mass of very small water droplets, 1 to 1,000 micron in size, a micron being a thousandth of a millimeter, or of ice crystals that float in the atmosphere when the temperatures are low. Condensation is the opposite of evaporation. Water vapor has a higher energy than liquid water, which in turn has a higher energy than ice. Thus, with condensation, freezing, and deposition, energy in the form of heat is released to the atmosphere. With evaporation and melting, heat energy is absorbed. Heat related to a change in phase of water is called latent heat, latente warmte. Okay, the water vapor condenses on small particles such as dust, sea salt, or chemical substances that float in the air and act as condensation nuclei, causing clouds to form. In fact, condensation of water vapor can only take place at a relative humidity of 100% if these particles are present. This is a picture taken in Le Bersac, which is near Serres in our fieldwork area in France, in the Haute-Alpes. And when you have calm conditions during nighttime, you get infrared thermal radiation of the Earth, causing cooling of the land. The cooling ground then cools the air above it by conduction, causing the air temperature to fall and reach the dew point. The dew point is the temperature at which you have 100% saturation of your air with water vapor. When the air cools further, you will get condensation and the formation of these low-hanging clouds, and this is called radiation fog. And something similar you can see in the Netherlands. This is near Apkoude, the Ronde Venen, and also here, due to calm conditions during night, thermal radiation, cooling of the air reaching its dew point, condensation setting in, you get this fog which lies at a layer over the landscape. And when you travel by car over the highway, due to the higher temperatures, due to the travel of the cars, there's no fog usually at the highway itself. And this is called grondmist in Dutch, or ground fog. The generation of precipitation, het ontstaan van neerslag. Precipitation starts when large water droplets or ice crystals fall to the earth due to gravity. In many clouds, the water droplets or ice crystals are not heavy enough to overcome the updraft of the air, which is the vertical upward movement of the air as described earlier. Also, precipitation may evaporate as it falls into the warmer air below the clouds. Thus, in order for precipitation to reach the ground, water droplets or ice crystals must become large and heavy enough to counteract both the effect of updraft and evaporation. There are two main processes that generate precipitation: in warm clouds and in cold clouds. In warm clouds, clouds with temperatures above freezing point, turbulent atmospheric mixing can cause water droplets of varying size to grow through a collision coalescence process. as schematized in the left part of this figure. By collision of rising and falling droplets in a cloud, the droplets coalesce to produce larger and larger droplets. Eventually, the droplets are large and heavy enough to overcome the air currents in the cloud and the updraft beneath it. This method of raindrop production is the primary mechanism in tropical regions. It typically produces drizzle, a fairly steady, light rain. In cold clouds, clouds with temperatures below freezing point, these can contain both ice crystals and supercooled water droplets. Supercooled water is liquid water that is chilled below its freezing point, without it becoming solid. As with condensation, the processes of freezing and deposition also need nuclei in order to get started. As freezing nuclei, the term includes deposition, ice crystals themselves are very efficient in attracting water vapor. The saturation vapor pressure over ice, which is the pressure of water vapor in close contact and equilibrium with ice, is only slightly lower than that over liquid water. But it is sufficiently lower to favor the ice crystals over the supercold water droplets in capturing water vapor from the air. The ice crystals attract the water vapor and grow larger. This reduces the amount of water vapor in the cloud. The air in the cloud becomes drier. The lower vapor pressure causes other supercooled water droplets to also evaporate, and then, as a follow-up, the newly formed water vapor to also deposit on the ice crystals. By this positive feedback mechanism, known as the Bergeron-Findeisen process, all supercooled water is thus effectively transformed into ice crystals that grow larger and heavier. And this is schematized on the right side of this figure. The feedback is called positive because the process of deposition itself, via another process, evaporation, strengthens the deposition. Also, the ice crystals may collide with other ice crystals and grow larger still through collision coalescence. Eventually, the ice crystals will have grown large and heavy enough to fall from the cloud as snow or ice crystals, or when they melt on their way down as cold rain. The Bergeron-Findeisen process is the dominant process for the generation of precipitation from cold clouds in the middle and upper latitudes of the Earth. We have concentrated on the physical process, but also Pseudomonas syringae, a bacteria, has been implicated as an important cloud condensation nuclei. Rising, expansion and cooling of air and the formation of clouds by condensation are preliminary steps for the generation of precipitation. The processes leading to the uplift of air and the scale at which these processes act may, however, differ. Following this, a number of different types of precipitation can be distinguished. Precipitation as a result of local heating of the air at the Earth's surface, as shown here, is called convective precipitation. This process is active in tropical areas and in the interior of continents. Convective precipitation is local and often intense, for example, during thunderstorms. When horizontal air currents are forced to rise over natural barriers such as mountain ranges, shown here, orographic precipitation may occur. Uplift of the air causes precipitation to fall on the windward side of a mountain range. This results in drier air on the descending, often warming leeward or downwind side of the mountain range, where a precipitation shadow, an area without or with only slight precipitation, is formed. For instance, in the US, in California, you have the Sierra Nevada mountain range, and then at a distance of 10 kilometers, the desert starts. When cold and warm air masses meet, frontal precipitation is formed. We have a cold front to the left and a warm front to the right. And we have it in side view here, and we have it in plan view here. And you can see from this plan view that the cold front and the warm front are part of a anti-clockwise movement, a cyclonic movement, the movement around a low pressure area on the northern hemisphere. What you can also see is that the cold front, the cold air has a harder job of moving underneath the warm air than the warm air has in moving over the cold air. So you get a very steep slope here between your cold air and your warm air, and you get a slope at a slighter angle here in between your warm air and your cold air. And this leads to rapid lifting and intense rainfall at the cold front, and at the warm front to a gradual lifting and cooling, and thus moderate rainfall of long duration. If you were to ask someone to draw the shape of a falling raindrop, he or she would probably draw something which looks like a teardrop, but raindrops are not shaped like teardrops at all. Rather, this is a photograph. This is the shape of your falling raindrop. It's flat at the bottom because the air has to move around it while the raindrop is falling. Here we see the shape of raindrops as a function of diameter. When they're small, they're still rounded, but when they get larger, they will flatten at the bottom, and when they get very large, they will split into two raindrops.